So a couple of months ago, I was looking at a file in the Ruby codebase, RubyCompile.c, and as the name implies, this file contains much of the compiler that's built into Ruby. And Faraz talked a little about the compiler yesterday. We'll go into it a bit more and what it means and what specifics are kind of within this file and why I was looking at it. But for now, I wanted to point out something that stood out to me. I was looking at this method, which we'll dive into a little more, and there was a parameter in here that I wasn't quite sure about at the very beginning. It was this int popped, and I saw it sprinkled all throughout the method. This is quite a big method, and it's very truncated here. But it was sprinkled all over in places like this. If not popped, if popped, different things going on there. And it wasn't so obvious to me at first what was going on, but once I read through the code quite a bit more and learned what was happening there, I thought it was really, really fascinating. And so I picked it for the title of this talk, Popping into Ruby. We're gonna pop in, we're gonna learn a little more about what's going on here, and specifically, we're gonna learn a little more about what this popped integer was and why it was so interesting to me. As Matt mentioned, just as a quick aside, I'm also the co-founder of WNB.RB, which is a women and non-binary global Ruby community of over 1,000 Rubyists. If you're a woman or non-binary person, please come join us. If you have colleagues who are women or non-binary people, please send them our way. We have a huge Slack space where there's a lot of really good conversations happening. Okay, so we can think of our Ruby program as cars kind of running. And I've driven a car plenty of times. I've never really looked under the hood. If you asked me what was there, I couldn't tell you much. But today, my hope is that we can pop out the hood of Ruby a little bit. And the gas is here not because there's something wrong, but just there's something interesting. There's a lot of interesting things going on under the hood of Ruby. And some of what we'll talk about today is how your Ruby code or your Ruby files become other things under the hood. They eventually become bytecode. Somewhere in the way, there's a parse tree. What's happening and how is this all going on? So these three things are related in that what you first do with your program is you write some Ruby code, and then it passes from the Ruby code to these different data structures, and eventually it executes under the hood whatever you've inputted. And we're going to begin with the first step here, which is getting from your Ruby code to this tree structure. And that step happens in something some of us may be familiar with, using something called a parser, which is what understands your Ruby code. And we'll go into the details for a little bit of how the parser is working and what it's doing to end up with this tree, which is a tree representation of any Ruby file. In fact, every Ruby file becomes some version of this tree at some point when you run it. And so to start, let's look at a small sample program and see kind of at a high level, hand waving a little bit, what the tree structure this is. It's a very creative Ruby program here. We have a class conference with one method, and all it does is give us return the string RubyConf. And so to see the parse tree, you can see the parse tree for any Ruby code you have. Similar to what Faraz was saying yesterday about being able to dump instruction sequences, you can also dump the parse tree. If you pass parse tree to this -- dump flag, and then pass in a Ruby file, you'll get back, and you can do this with any file in any code base, you'll get back exactly what the tree looks like. And as you can see, there are nodes here. Trees start with this scope node in Ruby, which is, scopes are also used for things like blocks or things like that can be more specifically scoped, but code always starts with the scope node. And all nodes have locations, which is really useful for tools that need to use the tree, right? We'll get into this later. What are other tools that could use a parse tree that aren't actually the execution of your code? And also they have lines to map with the locations. But we're going to focus a little more on the body of this scope node and kind of dissect what the tree is for this body. And we can see right away it's a class, right? There's a class node in this body, which is what we would expect given our program. So to drill more into that a little more, looking at our tree structure, we have this whole program is encapsulated within one class node, right at the top of our tree, right under that scope node. And then within the class node, there are a few children. The first one is the class path. You can see it here with node cpath. And it's what's called a colon node, which isn't necessarily the most descriptive node, but it's giving us an ID for that class. So we have a colon node. The cpath itself has this MID, a method ID of conference, right, which we know is the name of that node. And so there's this obscured another method ID that's a child of the colon node. And if we look a little more at the class node, it has also a super node, which in this case doesn't exist, right? It's a null node because there's no super to our class, but we could see clearly the use cases for a super node on there. It also has a body node, which again has a block node wrapping it, but the crux of what's within that body in our specific case is this defin node, or a definition node for our method definition. And if we look at that, that's this name method, right? Which makes sense. Within the class is the name method def name, and we have that as our green node here. And we can think about what we would expect to appear within the definition node, right? Presumably something with our string is going to come next as the body of that, maybe some other things. Maybe you can think for a second what should be children of the defin node. And if we look at it, we get again a method ID, right? Again, a name. For our defin node, the name happens to be name because that's the name of our method. And if we pull it up a little more, we also get args, right? So a method node, a defin node should have arguments. In this case, there are no arguments. So that's kind of this empty node we have here, but it still exists. And there's also a body node, which is the crux of what's happening within the method itself. And that string, the string RubyConf that we expected to show up here as a child node. And what's important to note here is that the abstract syntax tree represents all of our code, right? It has to represent all of our code. And why is that? It's because, as I was saying earlier, there's not only one consumer of our code, right? It's not just that we're using this parse tree for execution, but there are other tools that can also rely on it. If you think for a second, you might be able to think of what other things could use the parse tree that would just want the tree representation of your code, but not necessarily any executed representation. One you might come up with is a tool like RuboCop or linters or things like that, which just care about the actual code and not what happens when you run it. And so that's why this tree needs to represent a full thing. And critically, the tree can't have any optimizations, right? We can't speed things up at this level or kind of ignore some irrelevant parts of our code, because then tools like RuboCop or linters are just not going to have the full picture that they need to correctly do their jobs. Okay, so if you've been following Ruby News recently, you might have heard of another parser in Ruby News or seen code around it or something like that. It was formerly called YARP, so forgive me, please, if I refer to it as YARP. It's very much in my head as that. It's now called Prism. And there have been several talks on it, a lot of work done on it. I've been working on it. Kevin Newton ideated it and has been really leading the charge about it, and he gave a talk at RubyConfTH about it. You might have seen it in Ruby Weekly, or seen it on Ruby's bug tracker in various ways, or seen it on certain blogs or anything like that. And these are all talking about Prism, right? This new parser. But what exactly is it, and why did we need it, and what's important about it or different about it to the existing parser, right? Clearly we all know and write Ruby code, and clearly it's working, hopefully. And so why would we need to reparse it or parse it in a different way? And Prism actually doesn't generate the exact same parse tree. It actually generates a slightly different parse tree. The structs or the objects themselves are different for the nodes in Prism, but beyond that, what the objects represent is slightly different. If we look at this as just a small example, for instance, the args node wasn't really necessary in this case, right? It's just taking up space and it's not adding any value. It's just taking up memory. There are no arguments. We know there are no arguments. In Prism, for example, there's no args node. And then we tried to do a really good, thorough job of making Prism a little more understandable and maintainable. So one other small difference just from this little snippet, if you ran it through Prism, is instead of a colon node, you would get a constant read node, right? Because there's this constant and you're reading it. But otherwise, the node names are pretty much the same, and what they contain in this example are pretty much the same. And like I said, Kevin Newton has given a really great talk about this at RubyConfTH that I would highly recommend. And this is one slide from his talk. At the time, it was called YARP, Yet Another Ruby Parser. And he was talking about the 3 motivations behind YARP, why we wanted to build YARP. And I'm not going to go too deep into that, but I just wanted to talk about the first one because I think it's one that we'll really see applicable in our day-to-day when we use YARP. And it's error tolerance. So specifically, if you're not familiar with error tolerance as a concept, the word to really focus here on is tolerance. Right? Usually when we write Ruby code and there are a bunch of syntax errors, which I know none of us have many syntax errors in our Ruby code, we only get feedback on one of them, or the first one, and then there's no recovery, right? It doesn't tolerate any subsequent errors when we run our Ruby code through a syntax checker or something like that. So if we have this class syntax errors, and I'm going to give you a few seconds while I take a drink to look and try come up with how many syntax errors you can see in this code. Any thoughts? 3, cool. I don't know that I would have caught the third one. I'm very impressed. Yeah, so there's one after the ampersands, there's nothing, and we need something. We can't just trail on an ampersand. There's a missing end after the class node, after the class. And this B is out of place, right? It's a required parameter which needs to come before the optional parameters. And if we, so if we just ran this on Ruby, we would get syntax errors. There's also a flag you can pass to just check syntax and not actually run the code, which is ruby-c. And if we run ruby-c with this file, here's what we're going to get back. And I had these slides done, and Katrina's talk actually really made me think of this slide, because I think there are many people who are experts at Ruby who would look at these errors and know immediately what's going on. But I think if you're a novice, or if you haven't reached the point where you've seen enough examples of this that you know what's happening, it's actually pretty difficult to understand. The first one we get is unexpected local variable or method, and it's pointing to B. But if we don't really know Ruby, or we're new to it, or we haven't seen this error before, like, why is this unexpected, right? Can we not name something B? Can we not, like, what actually is going on here? And it's, of course, talking about this parameter order that we just discussed, but it's not doing so in a way that makes it, to Katrina's point, approachable to novices. It's doing so in a way that you need some expertise or experience, or maybe you'll just put this right into Stack Overflow or ChatGPT or something like that to help you understand, but it's certainly not obvious as the consumer of this error. And the second thing it's saying is syntax error unexpected end. Right? Looking at this, we can see we're missing an end. Is that what it's talking about? But no, it's talking about the trailing after the ampersand. It got this end, and it wasn't expecting the end because it was expecting something else. But instead of telling us, hey, I was expecting something after the ampersand, it's just saying the end was not what I expected. And to the point earlier about tolerance, it hasn't at all told us that we were actually missing an end, right? We just couldn't recover from the previous errors and tolerate them in a way that allowed us to get all the way to the third error. So as I mentioned earlier, Prism is a new parser, and I just wanted to show what Prism will give you with this file. So if you cd into Ruby Prism, it exists as a gem. You can use it as a gem. I'll talk in a moment about how it'll come in the future. You can just run bin parse to parse a file. If we run that for syntax errors, we get the following parse errors. The first one we get is unexpected parameter order, and it points us right, if you look at the location, it points us right to this B. It's saying that's an unexpected parameter order. Now, even if I'm new to Ruby, I think this gives me a much better picture of what I should do. Just switch the order of the parameters, right? Because that order was unexpected. There still presumably could be work to say, hey, unexpected parameter order optionals and requireds need to go in a certain order or things like that, but this is definitely giving me a much better start. The next error it's pointing to, it's saying expected an expression after the operator, and it's pointing me right here. Great, I know what's happening. It expected an expression and there was no expression. And note, it's not telling me expected a number or a string or something like that. It's an expression because it could have been any of those things. It's saying it can't parse the expression, right, because it expected something else. And then finally, it's saying expected an end to close the class statement, which is exactly this example of error tolerance, that it's made its way through all of this and is now telling me about the end that it's missing specifically for the class statement. So we're working really hard on Prism at the moment, and it's coming hopefully as a flag you can use in Ruby 3.3, so you'll be able to run your code using Prism. And as I mentioned, there are really three main benefits we've thought about. I've just shown off error tolerance. And on those three benefits isn't even listed things like speed or stuff like that. And it's already released as a gem that you can use. Okay, so we know we now have our code. It runs through a parser. It creates a tree. Those are all three things we've established so far. What's the next step here? What's the next thing that our code is going to become after it's this abstract syntax tree? It becomes this bytecode representation. And again, Faraz showed us a bit of what this looked like yesterday. And it's the compiler that turns it into that. And then from that code, it can run through some virtual machine or something like that, which will actually execute on all of the bytecode. But since Prism has created a slightly different tree, we presumably need a compiler for that different tree, right? Because the existing compiler, like I said, the underlying structures are different. The existing compiler won't just work one-to-one. And the reason I mention this is what I'm actively working on, what I'm so focused on at the moment, and why I was reading that RubyCompile.c. I was looking at the existing compiler to see how we can replicate a lot of its behavior or mimic its behavior for our new abstract syntax tree. And we don't want to create brand new bytecode. It's okay if the bytecode doesn't match exactly one-to-one, as long as it comes out to the same result, right? You could see cases where the different node structure could lead to slightly different bytecode, but it wants to be essentially similar. And we've already started merging a lot of this work and can continue to go node by node, implementing the compiler for Prism right into Ruby itself. Okay, so what does this compiler actually do? Let's try to understand that a little more, because critically, that's where this concept of popped is going to come up that I found so fascinating. So just as a reminder, this was the tree structure we had before in our AST at a high level. And this was a part of the method that I found so interesting. And what it actually does, this method, it's called ICCompileEach. It goes through all of the nodes from the top of the tree and has a big switch statement similar to a Ruby case statement or something like that on all of the different node types. And for each node type, it's going to tell you how to compile it, right? So you could imagine for a class node or something like that, it's going to do whatever it needs to do to a class node and then descend into the body node and call compile on that body node and keep kind of going down the tree. And as Faraz showed us again, he really previewed my talk in a wonderful way yesterday. We have this dump insns, which will show you the instructions for a given piece of code. And if we dump the instructions for conference.rb, for example, we'll get this set of instructions, which might look a little like gibberish to us at the moment, but my hope is it'll look not so much like gibberish to us in a few minutes. And it's filled with these things like a put nil. What is that doing? It's putting a nil onto the stack, But at a high level, it's calling right into this file called ruby-insns.def, at which point it assigns something to the value. So it's saying, hey, our value is qnil. We want this to be qnil. We want to put a qnil. Or something like a put string. A little more complicated here, but essentially what's going on is it's giving us a string for that value, right? It's saying, hey, I want to put a string that was the string value, whatever you passed, into val. And if we look at this snippet of instructions next to our tree, if we look for a second at a high level and see if we can kind of understand fuzzily a bit of what's going on here, like what seems to match, just take a second and look and see if you can see things that seem to relate to other things in here. Especially as they relate to our tree. Anything standing out? Do you see some stuff about a class or a string or stuff there? Yeah, I'm getting nods, but no vocal response, so I'm assuming you're just all focused on trying to dissect it. Yeah, so you might have seen this kind of first segment seems really similar to our class, right? And you can see it's referencing main at conference.rb, the main method. And we have stuff that we know has to do with our class here, right? Like we have this define class, which is getting the name of the class, or things like that. And then if we look a little further down at the next section, we kind of see our method here, right? We see define method around the name and the name method, and a put object around name. And we can see this has to do with the class, which used to be called user and is now called conference. And if we look a little further past this, we see this name at conference.rb, this method we know, the name method, and we see a put string in there, right, which we know has to do with our string or our string node there. And I want to focus specifically on this put string. I want us to learn a little more about what's going on in the put string and try kind of come up with a put string in isolation so we can use it to look into popt. So if we just wanted a string, right, what if, to start off with, to try and get just that string instruction, we had a Ruby file with just the string RubyConf, and we ran it through the parser. It's going to give us 2 nodes. It's going to give us that overall scope node, and then a child node, which is the string node, which is kind of what we expect, right? Just one scope, and all it has with it is a string node. And if we run that through the compiler, we're indeed going to get some bytecode. As I said, the compiler starts at the top and kind of iterates over. So the way it runs through the scope node is it's going to execute anything below and then give us a leave instruction to say, hey, get out of here, return. As it goes to the string node, it's calling this IC compile each. And the node I have here in this example is a node lit, which is a literal node, something like a number or a symbol. What we want to look at is node string, which happens to be almost exactly the same little case statement, except instead of put object, it's a put string. And indeed, if we run this through the compiler, we get this put string with RubyConf, which came, as we can kind of see right from here, right? It put string on the literal value on the node. It gave us a put string with that string RubyConf. But when we were talking earlier, we said the parse tree can't have optimizations, right? We can't have any optimizations at that step because there are other consumers. That's not true for the compiler. There aren't other consumers of this bytecode that need it unoptimized or need it in a certain way, which again is why Prism can create slightly different bytecode. So this step is really the compiler and optimizations, and you can drill down more into here, learn more about JITs or certain optimizations. In fact, there are a few talks I would recommend that go into this. Maple Ong gave a talk last year, 2022, at Uruko called Looking into Peephole Optimizations, which was one class of optimizations here. There's a ton of work on YJIT, a ton of resources to read about or code to read or things to learn there on some more compiler optimizations. John Hawthorne gave a talk at RubyConf Mini last year about making ISA fast, and he talked a bit more about the compiler and optimizations here. But the one I wanted to talk about today is this popt optimization. And so in order to understand what's going on here, I want to make our code a little more complicated, not substantially more, but I'm just going to give us a number after RubyConf. RubyConf 2023 on 2 separate lines. Now, what do we expect to get when we run this code? Thank you. 2023, yeah, exactly. Okay, so let's see, we run this through the parser, we get our full representation of nodes, right? A string node and a literal node, which was that node lit we talked about. String node first, literal node second. We run it through the compiler, and we just get put object 2023 and then a leave. Which begs the question, what happened to the put string? Where did it go, right? It was there, we put a 2023 afterwards, and it's no longer there. Well, if you look at this code, the string doesn't actually need to do anything, right? It's just a string, it's not being assigned to anything, it's not a parameter for anything, it's just like an extra string. I don't know why we put it in that code, but if we execute it, we don't want it to do anything, right? It's just more work. The program's not returning it, there's nothing that needs this string. So that's at its core what this popped optimization is getting at, and we'll look into how. But it's getting at not adding instructions for anything that's unnecessary, anything that could be, and here's where the name comes, popped off the code, right, is kind of irrelevant. And it's one way that the compiler is really, really working behind the scenes to catch us and to say, hey, I'm just going to figure out what out of this you do need and you don't need instructions for to the best I can. Definitely err on the side of giving you more instructions. It's not necessarily that fewer instructions is better, but if we could avoid adding an instruction that we otherwise would have to add, clearly that's going to give us some pretty substantial performance speed up and a little memory save on the compiled code. So let's get into it, right? It must have been going through this if not popped. Popped must have been true in this case of the string because we weren't getting that put string. And this popped is getting passed down the tree as we're kind of recursively calling this compile function over and over again. We're going to pass pop down as a parameter. But you can think that there are some cases where popped would actually be helpful or where we wouldn't want to pop something that we otherwise would have, right? I mentioned a few around method calls or things like that earlier on. Let's try to think of a few more where you wouldn't want to pop something that you might otherwise be able to pop. So in these examples, we're going to take the integer 2023 and see where we can't pop that integer. So if the entire program was 2023, the program needs to return that value, right? We can't pop it, we need to keep it. Or if it was the implicit return value in a method, again, we're going to need that value because if we call this method, we're going to need to know 2023. Or if we assign it to some variable, right? Even if we don't know if we're doing something with the variable, right? There could be metaprogramming or something like that that's going to use the variable. If there's a variable assignment, we need to generate an instruction for 2023. Or to the last example, if there's a method call, right? We don't know what the method call is going to do with this, maybe nothing, but it could do something, so we need to generate the instruction there. So these are all a few examples of when Ruby isn't popping things, right? When it couldn't. But let's think about when Ruby could pop things. And we want to put a value at the end of this example snippet, right? So that we know Ruby is going to return this value. Right, so it's got to return something. Let's just put a value there, and then any example I show above that value is going to be something that could be popped. And it's these literal values, right? A string could be popped, as we just saw in the previous example, or a symbol could be popped, or another number could be popped, or even an array that looks like this could be popped, right? It's a little more convoluted, but the array is going to call down compile on each thing, and it's going to pass popped. It's going to say, hey, this array isn't getting assigned anywhere. I don't need to actually make an array make an array for any reason, but I'm going to go down, I'm going to pass that this array isn't being assigned anywhere to everything down within the array and see if any of them need to generate instructions. And in this case, an arbitrary nil or a true or a false, none of these actually need to become instructions for any reason. So they're all going to get popped, this entire array. Or even you could imagine we could have a nested hash like this, where there are no side effects in this hash, right? It's just symbols and numbers and arrays. And so this hash is going to generate no instruction sequences. And if we indeed run this through our compiler, all we're going to get is a slight optimization on put object 1, right? Just put object 1 and then leave. For all this code, we're only going to get one instruction, which I think is a really neat way that Ruby is working behind the scenes for us, right? The internals are really mattering and doing a lot of work here for us and saving us some serious performance time on code like this, right? Because we're not doing all the unnecessary add a string instruction, add a symbol instruction, an integer instruction, create an array, right? Create enough space for an array, put 3 things in it, and same for hash and nested array and all of these types of things. But looking at this example again, I want to focus on the hash a little more. What if instead of this, we put something else within the hash, right? Super nested within this value on B, which is an array, we have another hash, and within that we have another array, and all the way in there we have a method call. We need to do this method call, right? Even if the rest of the hash is irrelevant, as we said, we need to do this method call. And it'll pass all the way down, right? Obviously, this isn't the exact parse tree, but it'll pass this pop value all the way down to the method call, at which point the call node will say, hey, I don't care about the popped value. I don't care about that because I know I'm a call node, and a call node I know cares about the values. So it's not going to pass the popped any further, and it's not going to be popped in this case. So we had several examples here of things that couldn't be popped, and several examples here of things that could all be popped. And looking at this and thinking about this as I was working on the compiler for Prism really got me thinking about how we think about the work we do in a day-to-day and what we think about that we pop and don't pop out of our actual day-to-day work, or actually daily, not even just the work generally, but what specifically we work on as it relates to programming. And I thought about one thing we definitely don't pop, right, at most of our companies is business logic, right? We definitely don't pop this. We don't ignore it. We pay a lot of attention to it, right? It's generally how our businesses run. We need to be working on our business logic. Or maybe some custom gems that we've written at our company, right, that are super relevant to the work our company is doing, and relevant to our business logic in some way. And maybe the performance of these things is really important, right? We pay a lot of attention to our business logic performing well and to our custom gems performing well. And even the security there, right? We can't allow any security leaks in these because these are the crux of our code. And then I was thinking a bit about what we generally, I know this isn't all of us, but what we generally tend to pop when we're thinking about this, what we don't really pay attention to or don't really work on. Things like open source gems, too often seen as just side projects and things that aren't crucial to our business or our day-to-day with our employer. Or things like Rails even that we don't really pay a lot of attention to. Or things like Ruby itself, right? Maybe we haven't peeked under the hood before. Maybe to our company and to us, this has been fully popped. My team actually works on all of these things, right? And we see real business advantages to doing so. I have here just 2 recent blog posts. I think they're 2 of the past few on my team's blog. Ruby 3.3's YJIT runs Shopify's production code 15% faster across the production code from working on Ruby itself, from not popping Ruby. Or another one here, 2 garbage collection improvements made our storefronts 8% faster. Which to me begs the question, why are we popping these things, right? Why are we not thinking of them as crucial to our business and crucial to our business logic? Can we instead imagine a world where we're incorrectly popping them, where these are actually avenues we could go down or learn more about or explore how they can benefit our team? Because as just demonstrated, they can have real impacts. And should we instead be moving things like open source gems or Rails or Ruby itself into this not popped column, right? Should we instead be learning more here and investing more here within our teams and within our real day-to-day work? And you might be sitting here thinking, sure, sounds great, but how would I even get started on that. I don't really know much about this. I've never really explored much. Because you've just sat through the last 35, 40 minutes, you actually have started to explore quite a bit, right? You've just listened to this talk, which I'm hoping you'll leave with a high-level understanding of what's going on with the parser and the compiler, terms that may not have been familiar to you. And I've sprinkled throughout this talk different resources or different links or different talks you can watch or things you can read to learn more if it's of interest to you. A few talks, a few blog posts, a few just general terms to Google and learn more about. And I'm hoping that leaving this talk and really as you think about what your company is working on and what you focus your day-to-day on, that we can engage a little more with these resources and start to learn more about how we can use what we've learned here today or things that we might learn in these resources to really actually benefit our companies and what we're working on. And if you want to make some contributions or if you're motivated by this to actually open some issues or some pull requests, Prism itself is very much open source, has many issues right now. As I said, we're working to release for Ruby 3.3, which is coming this Christmas. That's not a long time frame, and so the more the merrier in terms of help on that. If you're looking for a place to get started, this talk has given you definitely an overview that you could use to start making real contributions to Prism. I saw a lot of nods when I was talking about the error tolerance. I think most of you can see right away why that's going to help you and how that's going to help you as developers. And so my urge or my ask to you is to begin to devote more resources towards work like this, really with a hope that it'll help you and your company in the long run, as well as it's, to me, just interesting and fun. Thank you again so much for inviting me here and for listening.